Alright, gang, here we go. This is Chem 2, Unit 6, Part 1. We're talking about thermochemistry in this unit. Should be a lot of fun. This first little bit we're talking about is all about thermodynamics, kind of making sure we're all on the same page as far as thermodynamics go. If you've already taken physics, this will probably be a big refresher. So sit back and relax. If you have not, then you got a little bit of catching up to do, but that's alright. This stuff's pretty easy comparatively. Alright. So, energy, we talked about energy back in Unit 1, okay? And essentially, energy is just we kind of think about it as the ability to do work or transfer heat. And that's kind of the two things that we can do energy with, is work or move heat, all right? Transfer heat from one place to the other. Okay, and so this chapter is all about thermodynamics. We're going to talk about thermodynamics at the very front of this unit, okay, and it's the study of energy and its transformations. And then specifically, we're going to deep dive into what's called thermochemistry, which is the study of chemical reactions and then the energy associated with them. Okay, and we've kind of talked about this before, like when we talked about bond enthalpies and so on and so forth. We talked about that was a little bit of thermochemistry. We're just going to do a little bit more of that. Okay, so chemical energy is mainly potential energy. Okay, and so when we talk about chemical energy, essentially we're talking about the energy that could be given off or taken by atoms and molecules reacting with one another. Okay, and so this is potential energy. Okay, and the most important potential energy is this electrostatic potential energy. Okay, and they call it E, big E for energy, and then EL for electrostatic. All right, and this is the formula to calculate. We've looked at this before. Okay, but so essentially what we're saying is, these two like charges here are very close to one another, and because they're close to one another, they have a lot of repulsion, so they have a very high electrostatic potential energy. Okay, and then as these two like charges get farther and farther apart, their electrostatic potential energy goes towards zero. Okay, and then two like charges have very, very low electrostatic potential energy when they're close to each other, and then as they get farther apart from one another, their electrostatic potential energy gets closer to zero as they get farther and farther apart. All right. Just remember, unit for energy is in joules. Okay, this is how joules are made up because they're a combined complex unit, but essentially you just need to know that when we're talking about energy, we're talking about joules. Okay, electrostatic attraction, okay, is seen between oppositely charged ions. Okay, and so we've got these ions, positive and negatives, that are up close to one another, and when they're close to one another, they have a very negative electrostatic potential energy, and as we spread them apart from one another, their potential energy it gets less negative. Okay, so one thing that you need to get used to thinking about is that when chemical bonds are formed, energy gets released. Okay, so when we form chemical bonds, energy is released, and then when energy is consumed, chemical bonds are broken. So it always takes energy to break bonds. Remember a couple of videos ago we talked about how more than likely your biology teacher kind of told you a little bit a little half truth about how ATP breaking the bonds of ATP releases energy. Remember, that's not really true. You had to put in some amount of energy in order to break up ATP, and then in order to get net energy back, it reformed into ADP. Okay, first law of thermodynamics. Okay, energy can be converted from one form to another, but it is neither created or destroyed. All right, that's the basic middle school definition of the first law of thermodynamics, is that energy cannot be created or destroyed. Okay, and here's some examples. So in order to heat your home, chemical energy needs to be converted into heat. More than likely what happens is most of the houses around here is that we use natural gas furnaces, so the furnace actually burns the natural gas. Natural gas releases heat. It's an exothermic reaction. Okay, and so as it releases heat, the fan blows the hot air around the house. Okay, and so it's converting that chemical energy, that chemical potential energy of the natural gas molecules themselves into heat. All right, and then sunlight is energy and is converted to chemical energy in green plants. Chlorophyll with photosynthesis and all that stuff. Okay, so a couple of things that we need to make sure we understand whenever we talk about thermodynamics is this idea of the system versus the surroundings. Okay, the portion of the universe that we're studying, or whatever we care about, is the system. So in this case here, the hydrogen and the oxygen molecules are the system. We've got hydrogens, the white ones, and then oxygens, the red ones. Okay, and then the surroundings, they've defined as the cylinder, the piston, and everything beyond. So really, this inside volume is what we've defined as the system here. Okay, and then everything else is the surroundings. Everything else. Okay. So that's the system and the surroundings. Pretty basic, but it's very important. We'll kind of come to it a little bit here in a couple of slides. All right. Types of systems. We have three different main types of systems. We have open system. Okay, and this is a region of the universe being studied that can exchange heat and mass. So open systems can exchange heat and mass with the surroundings. All right. Closed systems can only exchange heat, not mass. Okay, so this example here, with the hydrogen and oxygen molecules, this is a closed system because heat can go through the metal containers of this cylinder and the piston, but the oxygen and hydrogen are stuck inside of it. Okay, and then isolated systems is a region of the universe that cannot exchange heat or mass with its surroundings. Okay, so essentially like bomb calorimeters, or really like well insulated places are isolated systems. Okay, cannot exchange heat or mass. Okay. Now, we also have to talk about this idea of internal energy. Okay, internal energy is the sum of all the kinetic and potential energies of all components of the system, and it's represented by a big capital E. You might have seen it in physics. We use a lot of time physicists use a big capital U. It's exactly the same thing. Now remember, kinetic is the energy of motion. Okay, motion. And then potential energy is a whole slew of different types of energies. Okay, so we could be talking about gravitational potential energy, how far above the ground are we? We could talk about elastic potential energy if you've stretched a spring or something like that. And then we could also talk about chemical potential energy, all right, the energy held within bonds, okay, so on and so forth. So internal energy is the sum of all of those energies that are going on. Okay. Now, the interesting thing is that generally internal energy is a really hard thing to measure the exact value of. Okay. Unless it's certain special cases, we don't know the magnitude of our internal energy. Okay. But the nice thing is we really don't care that much either. We really only care about how it changes. Okay, we'll look at this graph here in a second. So internal energy with a delta E, remember that delta means change in. Okay, so we're talking about change in internal energy. And so every time you see a delta sign, we always talk about final minus initial. So it's internal energy final minus internal energy initial. So this is one way of finding the internal energy of a system. Okay, and so essentially, if we want to know what happens to our internal energy, we start with H2 and O2, react to them to form H2O, and as they react, they're going to release energy because the final internal energy is at a lower state than the initial state here. Okay. So anytime our delta E, or our internal energy, is greater than 0, that means our final energy had to have been bigger than our initial energy. So the system absorbed energy from the surroundings. Okay, so that's this first line, or this line here. Okay, this blue one. Okay, and so we started at initial energy, and our final internal energy was a higher value. So we had to gain energy from somewhere. Okay, in order to be at a higher energy at the end. Okay, so it had to have gained energy from the surroundings. So our delta E would be positive. Delta E is positive when you gain energy. And here we go, we're negative. So we have an internal energy final minus internal energy initial. And you can see how, because initial is bigger, you're going to end up with a negative internal energy. So notice that our delta E is less than 0. That means it's negative. And so we've lost energy. Okay, our system has lost energy, and the energy has gone to the surroundings. All right. Okay. So thermodynamic quantities have three important parts. It's got a number. This tells you the magnitude. It's got a unit, and that tells you obviously what it's measuring. Okay, and then the sign. Now this is the new part. You're used to messing with numbers and units. The sign in thermodynamics is important. Okay, so a positive delta E results when the system gains energy from the surroundings, and a negative delta E results when the system loses energy to the surroundings. So remember before, just a couple slides ago, we talked about this idea of the system. Okay, and here's our system, and the surroundings. Okay. And remember, it's very hard to measure the internal energy of, like, the magnitude of the internal energy. Essentially, we don't really care about it because it's hard to measure or impossible to measure. So really, we only care about what is the change in, what's going across this barrier. Okay, so we really only care about what's going out or what's coming in into our solution. Now, the nice thing about chemistry, physicists get really funky about this, but in chemistry, generally it's defined as anything that's leaving our system has a negative sign. Okay, anything that's leaving the system has a negative sign, and anything being added to our system has a positive sign. So this would be some sort of negative, and it could be several different things that we'll talk about, and then anything that's coming in would have a positive value. Okay, so that's important to keep straight as we move forward. Okay, so the other way we can calculate our internal energy, or the change in internal energy, is Q plus W. Okay, now Q is the energy exchanged as heat. Okay, so this is the energy exchange or work, and it's lowercase w in our textbook. Okay, so inside this is our system. Okay, this is the interior of the vault. Okay, if they add heat and work to the system, the internal energy gets bigger. See, there's our internal energy. It got bigger as we added both, and our delta E would be greater than 0. If we lose both, our delta E would be less than 0. Life gets more exciting when we gain heat but might do work. Okay, so here's some, like, just very basic idea here. Okay, Q plus means the system gains heat. W plus means that there's work done on the system, or work entered the system. Okay, negative Q means that we lost heat, and the negative W means the system did work on the surroundings. Okay, so for E, remember, so this is our delta E. Okay, delta E, the positive delta E means we had a net gain of energy by the system. So whichever one was positive was a bigger magnitude positive than whichever one was negative if they're mixed. Okay, and negative means there's a net loss of energy, okay, by the system. So essentially that means whichever one was negative was a bigger magnitude than whichever one was positive. Okay, so let's do a practice problem here. Okay, it says calculate the change in internal energy for a process in which a system absorbs 140 joules of heat from the surrounding and does 85 joules of work on the surrounding. So we're talking about change in energy is equal to Q plus W. Okay, so that means our change in internal energy is equal to Q. All right, so this says in which a system absorbs 140 joules. So we have to think, all right, it absorbed 140 joules, where that means it came into our system, so that means it's going to be a positive 140. Okay, and then we're going to add in our work value, and it says and does 85 joules of work on the surroundings. So that means we lost energy to the surroundings, so that'd be negative 85 joules. All right, I forgot my joules here. So 140 minus 85 is essentially what we come up with. So 140, minus 85, we get 55 joules. 55 joules of work is the internal energy change for our system. Okay. Just a couple more things here. When heat is absorbed by the system from the surroundings, the process is endothermic, and you should be used to this, right? As if heat is absorbed by the system from their surroundings, this is endothermic. So like ice packs, you know, the non-temperature activated, the chemical energy ones, they steal heat from the surroundings. It's endothermic. Okay, when heat is released by the system into the surroundings, the process is exothermic. Both these terms should be pretty easy. You should know this stuff by now. Okay, one thing I think that's interesting about this idea is that, or about this little graphic that they have here, they've got some solution with water, and then the little chunk of potassium, they put it in there. Potassium will spark up. We did this in class. This is a lot of fun, right? And so you get a big exothermic reaction, lots of energy released. That's where the spark and the fire comes from. Okay. Now, but why did the water turn pink? Well, they probably, what they did is they used some sort of indicator, probably phenolphthalein. Remember, and you probably remember from Chem 1, phenolphthalein turns pink in the presence of a base, and potassium hydroxide is a base. Remember, and it's, in fact, you should remember that it's a strong base, and so it made turned our indicator pink because it's there. All right. Last little thing here is this idea of state functions. Okay. Essentially, state functions is a substance that has a magnitude that's independent of the path by which the system achieved that state. Okay, so an interesting one to think about, or like a really basic one, is internal energy. Okay, so if we had water that's at 25 degrees Celsius, it has a certain amount of internal energy, just straight up. Okay, now it doesn't really matter how the water got to 25 degrees Celsius. The water that is at 25 degrees Celsius, it could have come from 50 grams of ice water. Okay, and ice water started at 0, and then it had to take in energy, okay, in order to melt to become liquid water at 25 degrees Celsius. Or you could have started with near boiling hot water, the same amount of mass, okay, and it would have lost energy to its surroundings. Okay, and so internal energy is a state function. Okay, because it doesn't matter what path you take in order to achieve where you're at. Okay, so internal energy. Not everything is a state function. Okay, the idea is that this is your basic definition. Okay, it depends only on the present state, not on the path by which it arrived. Okay, so that means our delta E is only on the initial and the final, and we really only care about the difference of the two. Okay. Now, Q and W are not state functions, our heat and our work. Okay, in the two examples here, we've got a battery and we got discharged by being shorted out. Okay, so when a wire gets shorted out, it becomes very, very hot. Okay, and so this wire here lost all of its potential electric energy, and really its chemical potential energy gets lost as heat to the environment. Okay, so here's the wire, and it loses a bunch of heat going this way. Now, and so that's this guy showing your charged battery gets turned into heat. And then the other way is if we hook up that battery to a fan. Okay, when the fan goes, that motor is going to spin the blade, and so we end up with our battery loses some of its energy to heat, but most of it gets turned into work. Okay, so notice that it does matter. It loses a total delta E, and it didn't matter how that happened, but independently, heat and work were not state functions. Their values mattered upon the path that they took. Okay. All right, last bit here. Usually, the only work done by chemical or physical change is the mechanical work associated with a change in volume of gas. Okay, and so really essentially what this is saying is when we're thinking about work, for now, we're only going to be thinking about, well, what's happening to the volume of the gas that we're worried about. Okay, and so the system doing work on surroundings is equal to this value, negative P delta V. Okay, and so really we just care about, well, how much is our volume changing times the pressure that's pushing down, and that's going to tell us what our work is. Okay, and so we can figure out the work done by the gas with a chemical reaction with a setup kind of like this. We've got a little bit of zinc, and we flip this guy up. It falls into the acid, which produces hydrogen gas. Okay, and the hydrogen gas is going to increase the pressure up here, thereby pushing up on this piston, going that way. The piston increases, and because it increased the volume, right, we know that this system did work on our surroundings. All right, we'll just do a couple of practice problems here. All right, it says if a balloon is expanded from 0.055 to 1.403 liters against an external pressure of 1.02 atmospheres, how many liter atmospheres of work is done? So we know work is equal to the pressure times the change in volume. Okay, and so the pressure is 1.02 atmospheres. This is easy. Okay, and then we need the change in volume. Well, the change in volume here, change in always meaning final minus initial. So it goes from 0.055 to 1.403. So that means we'll take 1.403 liters minus our 0.055 liters. Now we have to think about this real quick. If we punch this in, we'll get 1.37 liter atmospheres. Okay. Now, but we have to think about this for a second. If we punch this into our calculator, or if we say this, well, gives us a positive work, and this implies that work was done on our system, but that's not what exactly happened. The balloon expanded and did work on the surroundings. Okay, so that means our work done had to have been negative, right? So we'll add that negative value, which gives us this, and this shows that we did 1.37 liter atmosphere of work on the surroundings. All right. All right. It's the next one here. Calculate the work in joules if the volume of a system contracts from 1.55 to 0.85 liters at a constant pressure of 0.985 atmospheres. Well, work equals pressure times change in volume. Okay, our pressure is 0.985 atmospheres, and our change in volume, well, it's final minus initial, so we go 0.85 minus 1.55. Okay, and remember now, our formula, remember we put that negative in there. We're going to keep that negative. As long as you remember to do final minus initial, you can keep that negative in there and life's going to be just fine. So we'll take 0.85 minus 1.55 and we'll multiply that by 0.985 and we get negative, and then times a negative 1, I forgot that part. So we get 0.6895 liter atmospheres. Okay. And then we think about sig figs. Well, this guy here has, if we subtract those guys here, okay, we'll end up with 2 sig figs. So this would really be 0.69 liter atmospheres. All right. So that's how you calculate work done by a system when it's changing gas. And that's it for our first little bit here into thermochemistry. Do your homework and your practice problems and let me know if you have any questions, and I'll see you on the flip side.